In this video, I'm going to focus on kinematics with calculus. Let's start with a review of your old kinematic equations. There are 3 of them. They're on most classroom formula sheets, and they're just different combinations of the same 6 variables over to the right in the white box. Make note that these equations only work if your acceleration is a constant value. However, if the acceleration is changing as a function of time, then these equations won't work and calculus will be required. So what is the difference between a constant and a non-constant acceleration? Let's look at a couple examples for each. Maybe we release a ball from rest at the top of a ramp, but the ramp has a constant slope. We'll expect this ball to pick up speed at a constant rate. This would be an example of constant acceleration. The same would be true of an object that we push with a constant force. If you look at the graph, the force is the same size the entire time, and this box will pick up speed at a constant rate as well. If instead we let the ball roll down a ramp with a varying slope, then the object will pick up speed at a varying rate. This would be an example of a non-constant acceleration. The same would be true of an object that we push with a force that increases its magnitude over time. This is known as a variable force, and it would also produce a non-constant acceleration. As it relates to graphs, we should already have an understanding of how to turn one kinematic graph into another. Here we're looking at an object that is depicted on the position time graph as accelerating at a constant rate. So we see a nice curving line. We already know the slope of this graph represents the velocity, and this slope is getting steeper and steeper. That means the velocity is getting greater as time goes on, and it would produce for us a nice linear graph as velocity versus time. Well, now we start over. We should already know that the slope of a velocity versus time graph is the acceleration. Well, this is a constant slope, so that would mean we have a constant positive acceleration. As we graph a versus t, we get a horizontal line. So analyzing the slopes will help us work from position to velocity to acceleration. In calculus, we want to know that analyzing the slope of a graph is the same as taking the derivative of the graph's function. So the derivative of a position function with respect to time will produce a velocity function with respect to time. Similarly, the derivative of a velocity function with respect to time will produce an acceleration function with respect to time. Let's start over, but work backwards. Now we're beginning with an acceleration graph. Again, we see it's a constant positive acceleration due to the horizontal line. Well, we already know that the area of this graph represents the change of velocity. If I were to look at 2 equally timed segments within this data, in this case A1 and A2, the area produced by each would be equal because of the horizontal line. And that would be proof of a velocity then that is changing at a constant rate, and more reason why we have this linear graph. Now we start over. We should already know that the area underneath the data of a velocity versus time graph represents the change of the object's position or the object's displacement. Again, we look at 2 equally timed segments of this data, A1 and A2, but now A2 would be much bigger than A1 because of the linear shape. There's more area enclosed in this segment because it's higher up than there would be here. So that would tell us that the object is changing its position at an increasing or a varying rate, and that would mean that we get a curve on the position time graph. In calculus, we want to know that analyzing the area of a graph is the same as taking the integral of the graph's function. So the integral of a velocity function with respect to time will produce a position function with respect to time, and the integral of an acceleration function with respect to time will produce a velocity function with respect to time. Let's look at an example, one for you to try. Here we have an object moving according to the position as a function of time expression on the middle of your screen. Our goal is to derive equations for the object's velocity and acceleration as functions of time. If you want to pause the video and try this yourself, I'll walk you through all the steps here in a minute. To get started, we remember that taking the derivative of this function with respect to time will produce a velocity function. Here I'm performing the derivative and winding up with my final velocity expression as initial velocity plus acceleration multiplied by time. Next, we remember that taking the derivative of our new velocity expression will produce our acceleration expression. After performing the derivative, we wind up with just the variable a. Couple things to point out here. First, with what I've boxed in green, you should recognize as your kinematic equations. We can use one to derive the other if we understand how derivatives and integrals correspond with our kinematic variables. Secondly, our kinematic variables only work with constant acceleration, and this is why our final acceleration expression worked out to be just some constant variable a. One other reminder is from our oscillations unit. There we went over a position as a function of time equation for an object undergoing simple harmonic motion. But because this is an equation of position as a function of time, we can apply our same derivative and integral rules to it if we are asked to produce things like velocity or acceleration as a function of time. Finally, I just want to point out that on your AP Physics formula sheet, the last page offers some calculus help. There are several derivative and integral reminders in this section. Most notably, they're helping you with the derivative and integral rules for trig functions, which are especially helpful with those kinematic equations from the oscillations unit.